Okay, so today we're going to study damped simple harmonic motion. And previously we have studied simple harmonic motions, okay, and then combination of simple harmonic motions, combination of simple harmonic motions along a line, combination of simple harmonic motion perpendicular to each other, and all those things we have studied. Okay, so today we're going to study damped harmonic motion. Okay, damped harmonic motion. So how the damped harmonic motions are formed? So look at here. If we connect one spring, if we connect a mass with a spring, okay, suppose this is not there, okay, so this is actually linear oscillator you have seen previously. Okay, when this band is absent, we call it simple harmonic motion. Now what we did in this case, we add a stick here, and then we dip it in a fluid, in a liquid. Okay, so when it try to oscillate, so it will be, this act as a damper. So this is called damped harmonic oscillation. Okay, so a pendulum will swing only briefly underwater because the water exert on the pendulum a drag force that quickly eliminates the motion. A pendulum swinging in air does better, but still you see, even in air resistance is also there. So actually all motions are, even a mass spring system, there is also a damped oscillations, but to stop it needs a longer time. Okay, so for the time being, for a small momentarily, we can assume this one as a simple harmonic motion if the mass spring system is in air medium. Okay, like this. Okay, so when the motion of an oscillator is reduced by an external force, the oscillator and its motion are said to be damped, and this system is called damped harmonic oscillator. So an idealized example of damped oscillator is shown in this figure. I've already explained. So where a block with mass m oscillates vertically on a spring with a spring constant k, and from the block a rod extends to a vein that submerged in a liquid. Okay, like this one. So this mass spring system, we can consider this one as a simple harmonic oscillator. So when we connect this one and we dip it in the water, so that acts as a damper. So this is the damped harmonic oscillator. Now at first we are going to establish the differential equation of the damped harmonic motions. To establish the differential equation of this damped harmonic motion, we will use Newton's law. Okay, according to Newton's law, you know that F equal to m, second law of motion, F equal to ma. Okay, so F is the total force acting on the system. Now in this case, this is subscript actually. This is F damping force is Fd. F subscript d is proportional to the velocity. Okay, you can check this one. In a windy day, if you just walk against the wind, okay, you will rarely feel some obstacle. Okay, but if you wanna run, you will see strong obstacles are there. Okay, that means this damping, it actually is proportional to the velocity. If you wanna move faster, so the air will give larger resistance to your motion. So that means damping force is proportional to the velocity. So damping force Fd will be, this is the proportionality constant, but damping constant minus Vb. Okay, so now what are the total force acting on the system? The force on the block from the spring is, it will give a restraining force, which is also proportional to the displacement. So Fs equal to minus Kx. So total force acting on the system is minus Kx plus minus Bb. So that's the total force. And total force is equal to Ma. So total force is minus Bb minus Kx, that must be equal to Ma. Okay, so now what is A? A is V square x dt square, so that is Ma. And if we bring this one all in the right hand side, so this will be plus B, and velocity is dx dt, and then plus kx must be 0. Okay, and if we divide both sides by m, so this will be d square x dt square and b by m dx dt, k by m x equal to 0. And if we choose b by m as gamma, so we choose b by as gamma, and from our previous knowledge, we know that k by m is nothing but omega naught square. Okay, so the equation become d square x dt square plus gamma dx dt. So this is the differential equation of a damped harmonic oscillations. If you compare this one with your simple harmonic oscillations, in simple harmonic oscillation, this term is absent. Okay, this term is not there. In the simple harmonic motion, this term is missing. So this is the damping term. Okay, without this equation become the equation of a simple harmonic motion. And this term appears because if you look at the previous space, because of the presence of this vein. Okay, this is the damping factor. So without damping factor, this become a simple harmonic motion. Okay, so now as before, we need to find out the solution of this differential equation. So in your math class, you have studied how to solve the differential equation. Okay, so to solve differential equation, you need to choose a trial solution. Okay, before that, what we did, we shall at first you see our previous equation is d square x dt square plus gamma dx dt plus omega square. So we will convert this one in a complex plane, okay, jet plane. Like we'll do this by the complex exponential method by assuming that x is the real part of a rotating vector jet. Suppose we choose a rotating vector jet, okay, it is rotating. So, and a real part of z is actually x. So in that case, in the complex plane, the equation will become d square z dt square plus gamma dz dt minus equal to 0. And as we choose the trial solution as z equal to a e to the power j pt plus alpha. J is you have studied the imaginary number, j equal to minus root over 1. I don't know, you might have studied this one with I, but in physics, we do not use I because I is another important factor in physics, which is current or electrical engineering is current. So instead of I, we use J, A to the power J pt plus alpha. And then you differentiate this one once, dz dt, at first you will find dz dt, and then you will differentiate again d square z dt square. Okay, what is dz dt? Dz dt is a to the power j pt plus alpha. So it will be again if you differentiate an exponential function, e to the power x, differentiate e to the power x is e to the power x. So it will be z a e to the power, it will be a e to the power j pt plus alpha, and then you are differentiating with respect to t, so jp term will become here, jp. Okay, and if you differentiate again, another jp will be there. So jp is equal to j square p square. J square equal to minus 1. So finally, if you substitute this one, so this common factor will be this one. Okay, so common factor is this. If you take this one common, this equation become, if you substitute dz dt d square z dt square in this equation, it will become minus p square and then plus jp gamma term is here, and jp will come from, you differentiate it once, jp, and then omega square equal to 0. So this is when the multiplication of two terms is 0. Actually, this is not 0. So this term has to be 0. Now this condition is one involving the complex number, and it really contains two conditions. We know that the real part of the right hand side must be equal to the real part of the left hand side, and real part of the imaginary part of the left hand side must be equal to the real part of the right hand side. So if we apply that one, it cannot be satisfied because the quantity P is purely real. But if you look at here, we can see it's imaginary. Okay, because the term JPY would then be pure imaginary quantity with nothing to cancel. So we therefore put P as another complex number, P equal to n plus Js. If P equal to n plus Js, P square will be n plus Js square, which is n square plus 2jns, and then it will be J square S square plus J square S square. J square is minus, so minus S square. If you substitute the value of P square and P in this equation, so this equation will become n square, this one. Now we will equate real part of the left hand side must be equal to the real part of the imaginary. So real part is this one must be 0, and imaginary part is twice ns plus n gamma, that must be equal to 0. So if we solve this one, from here n cancel out, so s will be gamma by 2. Okay, s will be gamma by 2. And if you substitute the value of s in this equation, okay, you can find out n square will be omega naught square minus gamma square by 4. So you can see the n has a dimension of omega. Okay, when the damping factor is 0, this omega become omega naught. Okay, now our solution is a e to the power j pt plus alpha, and p equal to, we have chosen, our solution was z equal to a e to the power j pt plus alpha, and p is n plus js. Okay, so finally it will be z will be a e to the power j nt plus jst plus alpha. Okay, and j if you multiply it, again it's j square, so minus, so a to e to the power minus st will become here, and e to the power j nt plus alpha. Okay, and s is gamma by 2, or the real part of this is the complex number, so real part is the x1. So real part, you know that e to the power j nt plus alpha is actually Euler's formula, this one, cos of nt plus alpha plus j sine nt plus alpha. So real part is actually a e to the power minus st cos of nt plus alpha, and s is gamma by 2. So x will be a e to the power minus gamma by 2, and then cos of n, you can choose n as omega. So it will be omega t plus alpha, where omega is actually this one, omega naught square minus gamma square by 4. And what is omega naught square? Is k by m, we have seen previously. And what is gamma? Gamma is b by m, so it will be b square. So so this is the solution of the damped harmonic oscillations, where omega will follow this equation. Omega equal to square root of, omega is square root of this one, k by m minus b square by minus b square by 4 m square. And if you plot, you see, if it is simple harmonic motion, so and if it is cos function, it will be like this. So it will be simple harmonic motion. So amplitude will remain all the time same. But in this case, it is a sinusoidal function, okay, repeating function. However, the amplitude will decrease gradually. Okay. If we plot x as a function of t, so look at here, amplitude will exponentially decrease. Finally, it will become die out. Okay. So the curve in adjacent figure is drawn for a case in which decay of the vibration is rapid. If, however, the damping is small, the motion approximates to simple harmonic at constant amplitude over a number of cycles. So an amplitude will follow this formula. Okay. So if amplitude decreases means the total mechanical energy of the simple harmonic oscillator we have studied, which is half of k s square. A is the amplitude. Now, previously, in case of simple harmonic motion, amplitude remained constant, but in this case, amplitude is exponentially decreasing. Look at here, exponentially, it is decreasing exponentially. So, mechanical energy as a function of time will be half k n naught square e to the minus gamma t. That means energy will also decrease exponentially. So that is why ultimately it will stop. However, in case of simple harmonic motion, for an ideal simple harmonic motion, it should oscillates forever. Okay, but in this case, it will stop after some time, it depends on the damping factor. Okay. Okay, so today we have studied about damped harmonic oscillator. Okay, so we need to study forced vibration as well. Okay, forced oscillations. Okay, so let's study. Let us study forced vibration and resonance. Okay, let's just talk.